Okay, before we begin, can I just get confirmation that you guys can hear me clearly? Perfect. Okay. Sorry for the delay. I'm a bit delayed this morning, but nevertheless, let us begin. Okay, so we're going to continue with exponents, which is where I believe we left off last time. Yeah, and then we're going to move on to do some patterns. Okay, and then I think we're done for all the topics for the term, so maybe next week. Can I just get a double checking on when you guys are writing? Maybe some of you have written already. Maybe some of you are writing this week. Maybe some of you are writing next week. Tuesday, Wednesday, Tuesday, this weekend. Okay, a lot of people are writing this week. Okay, so perfect. So hopefully we'll be done in time with all topics for you guys' test, right? And for those who are writing maybe the following week, then we can do a revision session. Okay, so let's get started, right? Exponents. So last week we went through the rules of exponents, right? I think we finished up until simplifying surds. Maybe we need to discuss fractional exponents and rules of surds. Okay, so before we do some questions, we're going to quickly recap rules of exponents and complete rules of surds, right? So rules of exponents. Okay, let's have a look at the first one quickly. We said that when we have the same base, for example, here we have, one second, let me connect this. Okay, so for example, here we have the base of A. Okay, so same base in multiplication, it doesn't matter what our exponents are. Never heard of surds. Okay, so surds are basically square roots. Okay, so we'll go through it in a bit. Okay, so when we have the same base A, and again, it doesn't matter what exponents we have, but we can add the exponents. Okay, so that's really important for us to remember. Same bases in multiplication, we can add the exponents. Okay, so a to the x times a to the b results in a to the x plus b. Okay, in one exponent, we add them. And we also need to realize that we can work backwards. So for example, if we have b to the power of x plus y, we can have b to the power of x times b to the power of y. Okay, so similarly, when we have division, we can subtract the exponents. Okay, we can subtract the two exponents, keep one base and subtract the exponents. And we need to note we can work backwards. So if we're given b to the x minus y, okay, the first thing we should actually note, and it's more common to use, is we can actually like how I indicated here, right? It's like having x plus negative y. So then you can have b to the x times b to the negative y. Okay, so you're just keeping it all in the numerator, basically. Alternatively, you could even write it as the rule states as a fraction. Let's look at number 3. Okay, number 3 is a power to a power. So we have a to the power of x, and that entire term to the power of b. Okay, so in that case, when we have a power to a power, okay, we multiply the exponents. So a to the power of x times, a to the power of x to the power of b becomes a to the power of x times b. Okay, so if we look at this example, just say if we're working backwards, right? If we have b to the power of 10c, we can separate it as b to the power of 10 to the power of c. Alternatively, b to the power of c to the power of 10. Right? Practically, if we have to do an example, we could have okay, 2 to the power of 3c. Okay, so if you want to, you can put it as 2 to the power of c to the power of 3. Or to simplify this, we could actually put it to 2 to the power of 3 to the power of c, and then this becomes 8 to the power of c. So 2 to the power of 3c is actually 8 to the power of c. Okay, so that's working backwards how we can simplify it. Okay, number 4, a to the 0 is equal to 1. So basically anything to the power of 0 is equal to 1. We said x to the power of 0 is equal to 1, 17 to the power of 0 is equal to 1, 1 billion, I think, 1 trillion, I think that's 1 trillion to the power of 0 is equal to 1. So anything to the power of 0 will give you the answer of 1. Then we talked about a negative exponent. Okay, whenever we have a negative exponent, we can make it positive by flipping it. So either taking it to the denominator or taking it to the numerator, depending where it's negative in. So we did an example here okay, where we had b to the power of -3 times a to the power of 2 divided by c to the power of 4 times d to the -2. And if we wanted all the positive exponents, right, we could take the negative ones from the numerator and put them in the denominator, they'd become positive. We would take the negative ones from the denominator and put them in the numerator, and they become positive, just like what we did with b, where we took b to the bottom, and it became to the power of +3. And then d, we took it to the top, where it became to the power of +2. Alternatively, if you don't want the denominator, you can just take them all to the top. All right, remember, for example, these are positive in the bottom. So when they go to the top, they'll become negative. Okay, so that's two ways of expressing it. Then we discussed when we have a product to 1 power, meaning when we have a multiplication, two terms multiplied by each other, and the entire multiplication is to a power, we can basically distribute that exponent to each term. So a times b whole to the power of x becomes a to the power of x times b to the power of x. Okay, I see a hand raised. If you have any questions, just ask them in the chat Q&A or YouTube chat. Okay, so yes, it can become a to the power of x times b to the power of x. Okay, so we can basically we're distributing that exponent. Okay, then we just did an example. For example, 7 times a squared became 7 squared times a squared, which is 49 times a squared. Okay, and yeah. What about number 5? Okay, then if we have a fraction to 1 exponent, like a division basically, then we could distribute the x to each term. One in give the numerator an exponent and give the denominator an exponent. Okay. Okay, how many of you have done surds in class? How many of you know what a surd is? Or have like done practice or done the topic? Okay, so you should have done some bit of surds, you know. So that's why I'm going through them, because you should have done some bit of surds. Okay. So for the person that said number 5, do you not understand number 5? Okay. So then we talked about simplifying surds. Okay. We have to write it as a product with a perfect square. So each number, right? Each number, right? What we do with each number is we try and find factors of that number. Okay, factors are numbers that go into another number an exact amount of times. And one of the factors needs to be a perfect square so that we can take the perfect square out. Okay, so if, for example, here, if we look at this example, right, we said square root 96, that can be written as 49 times 2, which specifically chose 49 as one of its factors because 49 is a perfect square. Then we can use surd rule 1 to separate our surds. It becomes square root 49 times square root 2, and then square root 49 has an answer of 7. Okay, let's talk about the fractional exponent. So basically, the rule is as it states. Whenever you have a square root or a cube root, whatever root, okay, let's just say we have y cubed inside of a square root. So whenever there's no number on the outside of a surd, we always just assume that it's a 2. Okay, so basically you can simplify this as y. The exponent inside of the surd becomes the numerator of the exponent of our new base, and then the number outside becomes a denominator. So this can be simplified to y to the power of 3 over 2. Okay, similarly, if I just have the square root of x, okay, the square root of x can actually be written as, because there's no exponent for x, so it's assumed to be 1. And there's no number outside of the surd, so it's assumed to be 2, right? It's the square root. Okay. So this becomes x to the power of 1 over 2. Okay, that's the fractional exponent. Let's move on to surd rules number 2 and 3. So number 2, similar to number 1. So number 2 basically states that when you multiply two surds, okay, you can put them all under one surd with multiplication. So square root of a times square root of b can become square root of a times b. Okay, so whenever you're multiplying two square roots, it doesn't matter what's in the square roots. You could put it under one square root and then multiply what's in each square root together. Okay, so square root of a times square root of b becomes square root of a times b, and then working backwards also is important. If you have square root of x times y, you could write that as square root x times square root y. Okay, so just how we simplify the surd, we utilize that rule where we separate it into two different surds. Okay, let's not worry about number 3. That's fine. It's a bit higher level, and that also shouldn't matter as well. You'll just know the basic 2 rules of surds. Okay. Let's go ahead and do some questions. Which should we start on? Okay, let's start with these. 1 second. Okay, so we just asked to simplify the following. Okay, so right here we have 3 to the 8 times 3 to the 1. Whenever there's no exponent, it's an invisible 1, times 3 to the 3. Okay, so here I'm just going to write it with dots. Maybe some of you prefer the dot for multiplication. 3 to the 3. Now remember, so exponent rule number 1. When I have a to the power of x times a to the power of y, so I have the same base in multiplication, I add my exponents. So here I can simplify this to 3 to the power of 8 plus 1 plus 3. I can add up my exponents. It becomes 3 to the power of 12. They didn't actually want you to get the answer here. They just want us to simplify it. Okay, just practicing the rules that we just learned. As you add all of it together, yes, you're adding the exponents together. So for example, here I have 2 to the power of 5. I'm going to rearrange it. Okay, I'm going to rearrange it, right, to group the 2's. So I'm going to have 2 to the power of 5 times 2 to the power of 3. 1 second. Two to the power of 5 times 2 to the power of 3. Okay, I think this is called the commutative property of multiplication. I'm not sure if we did it in the beginning when we discussed whole numbers, maybe, but it doesn't matter about the order in which you multiply. All right, you could change up. If you only have multiplication, you could change up the order. So that's exactly what I'm doing. I'm just grouping the 2's and then I'm going to group the 5's. 5 to the power of 1 times 5 to the power of 4. Okay, just rearrange that. Now I can simplify the 2's and I can simplify the 5's separately. Okay, so I can say this is going to become 2 to the power of 5 plus 3. 2 to the power of 5 plus 3 times 5 to the power of 1 plus 4. Okay, I hope we're seeing that and that makes sense. So this becomes 2 to the power of 8. Okay, times, this is not great. 1 second, sorry. Okay, so this becomes 2 to the power of 8 times 5 to the power of 5. Okay, again, they didn't want us to get the answer yet. They just want us to practice our rules. Okay, so we have similarly, again, m times m to the power of 2 times m to the power of 3 times m to the power of 5. This becomes m to the power of 2 plus 3 plus 5, which simplifies to m to the power of 10. Okay, 3 to the power of 4. Okay, let's have a look at this, right? So now we have multiple variables. Okay, okay, actually one is like a constant. We have a number base and we have a variable base. The person that's typing in the chat, I don't understand what you mean by the numbers. I'm very confused. What do you mean by 1? I don't understand what 1 means. Please be more specific with your question. Okay, so yes, in this case, what I could do is, again, commutative property of multiplication. So this is basically 3 to the 4 times b to the 6 times 3 to the b, or 3b, sorry, times, or actually times 3 to the 1 times b to the 1 times 3 to the 2 times b to the 7. Okay, which is equal to, I can group my 3's if I like. So 3 to the power of 4 times 3 to the power of 1 times 3 to the power of 2. Okay, so I'm just grouping the 3's. Because again, it's multiplication. When you only have multiplication, okay, when you only have multiplication, then it doesn't, the order in which you multiply your terms does not matter. Okay, so multiplied by b to the power of 6 times b to the power of 1 times b to the power of 7. I'm grouping the b's. And I can simplify, because that's multiplication of the same bases, I can simplify my bases. Okay, I'm going to work here. Basically, 3 to the 4 plus 1 plus 2 times b to the 6 plus 1 plus 7, which is equal to 3 to the 7 times b to the 14. Question number 1. Okay, what about question number 1? We explain question number 1. Okay, so with question number 1, we are basically using this rule. Okay, this rule is a to the power of x times a to the power of y results in a to the x plus y. So whenever we have two terms with the same bases and different exponents, as can be seen here, we have same base, a to the power of x. Adding exponents, how does it work? Okay. Okay, so I guess I'll just re-explain this rule. I think that would encompass your question as well. So I have a to the power of x. Okay. So again, I have multiplication of the same base. Okay. So whatever my base is, as long as it's the same, okay, as long as my base is the same. So for example, I could have 5 to the power of y times 5 to the power of q. Okay. So irrespective of what my exponents are, provided I have the same base and it's multiplied to another term with the same base as the previous, I can simplify this under one base. Okay, so instead of having two different terms, I could simplify it to one term, keeping the base the same as 5. And then I take each exponent from each term and I add them. So I'd say y plus q, now under one base. So this basically becomes 5 to the y plus q. So if I do another example, if I have 10 to the power of 4 times 10 to the power of 3, again, I identify here, oh, I have the same bases. My bases are 10. They are in multiplication with one another. So what I can do is I can write them all under one base. Okay, and each individual exponent from each term, I can add them now for this term here. It's 10 to the power of 4 plus 3, which basically then becomes 10 to the power of 7. Okay, you're adding them inside of the exponent, if that makes sense. Okay, I hope question 1 makes more sense and the person who asked the other question also understands. Okay, let's move on. Let's do some, okay, I'm going to skip out on the easy examples. I'm going to go do some hard examples. So let's have a look at a basic one. We have 2 to the power of 11, okay, over 2 to the power of 6. Now, here we see this, we have the same base, however, in division. So we need to remember the rule that said, if I have the same base, so if I have x to the power of 5 over x to the power of 2, what I will then do, okay, is I will write it under one base and subtract the exponents. I will say top minus bottom. I will say top minus bottom. Okay, sorry. So similar to how when they were in multiplication, you added the exponent. Here, when they are in division, you are going to subtract the exponents. Okay. So in this case, I'm going to write one base, which is 2, because it's 2 to the power of 11 divided by 2 to the power of 6. Okay, and then what will be my exponent? What would I write as my exponent? Someone tell me. Correct. All right, 5 or 11 minus 6. So 11 minus 6, and then we get 2 to the power of 5. So we can now, these are maybe more simplifiable. Again, they don't want us to get the answers here. They just want us to simplify. Simplify. However, the answer is 32. They just want us to simplify. Okay, let's skip out on these examples. Let's have a look at number 7. Okay, so how do we go about simplifying something like this? Okay, so it's actually a lot easier than it looks, right? And you actually know all the rules already. So firstly, what you're going to do is you are going to simplify, let's just say the like terms together. Okay, so for example, right, how much marks is that? That would be like a 2 mark, like a 1 or 2 mark question, the previous question that we did. Okay, that was just, they probably not going to ask such a simple question. They'll ask something like this where it combines all the rules and it will be like a 3 or 4 mark question. Okay, so yes, when we have a term like this, we can see that on top, okay, we have only multiplication. It's 12 times a to the 8 times b to the 7, and then divided by 3 times a to the 3 times b to the 4. In this case, because there's no addition, okay, we can simplify from top to bottom. So again, like I said, right, what you're going to do is you're going to simplify your like terms, okay, together. So you're going to simplify the constant terms or the actual numbers, right? Then you're going to simplify each variable separately. So you're going to simplify a together, then you're going to simplify b together. Okay, so like I said, it's a lot easier than you think. Why I said that is because you can do each one individually. So you can divide the numbers. So you can even put in your calculator. You should know what 12 divided by 3 is, right? So 12 divided by 3 is 4. So because it's 4, as in like 4 over 1, I'll write it on the top. Okay, then I have 8 to the 8 divided by a to the 3. So now this is rule number 2. What is rule number 2? When I have the same bases, and I have the same bases in division, I can write it all under the same base and subtract the exponents. So a minus b. So in this case, it's going to be a to the 8 minus 3 times. Now I'm going to have b to the 7 minus 4. Okay, the top minus the bottom. So in this case, okay, there's no denominator because all the numbers are going to go to the top. So it simplifies to 4a5 b3. Correct. To the person that got it correct. Well done. Okay, so that's an important example. Hope that makes sense. Let's have a look at some other ones. Okay, let's have a look at this one. All right, just to practice what we call a power to a power. Okay. Oh, man. Okay, so here we have in brackets 2 times 3 to the 2 to the power of 4. Now, I just want to clarify, this is not equal to 6 to the power of 2 to the power of 4. You cannot multiply the 2 with the 3. The reason for that is because of BODMAS. Actually, let's just, I don't know which one you guys learned, but BODMAS would make more sense instead of using operations, where we have brackets, exponents. We always have to simplify exponents before multiplication. Okay, we always have to simplify exponents before multiplication. So in that case, we'd have to do this calculation first, okay, before we do that calculation. So we cannot say 2 times 3. This multiplication will take place after this takes place. So if you want to simplify this, it will become 2 times 9 to the 4, which is 18 to the 4, which is completely different to 6 squared to the 4. Okay, I just wanted to clarify that. Okay, but we're not going to do that. Why? Because we're going to distribute. Okay, we're going to distribute the 4 because to practice our exponent rules. All right, so here we have a power to a power. So what do you do with a power to a power? You distribute it to each term because we have a product. Okay. Yeah, okay, you learned BODMAS. BODMAS is it's the same thing. Okay. BODMAS is operations. One of the operations would refer to our exponents. Okay. But either way, you should know that exponents comes before multiplication. Okay. So yeah. So again, right, we have a product. So this rule here is actually like a times b to the power of x. This is equal to a to the power of x times b to the power of x. Okay, so that's exactly what we're going to do. We're going to take the 4 and we're going to distribute it. Okay, then we also have another rule actually. All right, the second rule here is a power to a power, because we're basically going to have yeah, we're going to have 3 to the 2. Okay, now let's learn it in terms of the rule. The rule said that if I have a to the power of x to the power of y, this becomes a to the power of x times y as one exponent. Okay, so in this case, right, I can distribute the 4. So I'm going to give the 2 a power of 4, and I'm going to give the 3 to the 2 a power of 4. So it's going to become 3 to the 2 whole to the power of 4. Hope that makes sense. Okay, so I gave each one the power of 4. Okay, now I'm going to have at the bottom 2 to the 2 times 3 to the 10. Okay, now let's simplify this. No, it did not. So no. So what do you mean by no did not? Did not do bad math. Isn't it 2 plus 4? No, it's not 2 plus 4. Okay, remember you add when you have the same bases. Okay, when you have a to the power of x times a to the power of y, when you're multiplying two terms with the same base, okay, when you multiply 2 terms with the same base, that's when you add the exponents. Okay, 2 terms with the same base, that's when you add the exponents. Okay, so that's not, you don't multiply in this case. All right, sorry, you don't add. In this case, you would multiply. Again, we're following this rule, which I think is rule number 3, if I'm not mistaken. Let's just go double check. Power to power, yes, it's rule number 3. All right, this is rule number 1. And I think I labeled this is like rule number 6 or something. Okay, so we're following rule number 3. Okay, because here we're following rule number 6 and rule number 3 at the same time. So let's do it without the squared. If I just had to have 2 times 3 to the power of 4. Okay, so I have a product, a multiplication, okay, to the power a multiplication, and the whole multiplication is in brackets, and the entire brackets is to the power of 4. Okay, in that case, the way to simplify it is to give each term inside of the bracket the power of 4. So you'd simplify this to 2 to the power of 4 times 3 to the power of 4. Okay, that's basically what we're saying. And now when we add the squared, so I have 2 times 3 squared to the power of 4. Now my term is 3 squared. Okay, so I will do the exact same thing, but now I will just consider the squared. So I'm going to have 2 to the power of 4 times, it's just going to be 3 to the power of 2. So I'm not changing this term. I'm keeping it as 3 to the power of 2. I'm keeping it exact the same. And I'm taking that term and I'm putting it to the power of 4. The reason I put brackets is because the reason I put brackets is because it does because we have two exponents. Okay, so not to confuse them. Type thing. Okay, so we are doing essentially the same thing in here that we are doing here. And it's one of the laws of exponents. Okay, you distribute the power basically to each term in the multiplication. Okay, so in this case, it's just that we have one of our multiplication terms is actually an exponent. So we'll take that exponent and put it to the power of 4. Okay, now this one specifically, to simplify this one, this is another rule. It's again, whatever the rule number, it doesn't matter. But whenever you have a power to a power, so a to the power of x to the power of 5, let's use numbers. A to the power of 2 to the power of 4. This has to simplify as a to the power of 2 times 4. It's called the power to a power. We don't add these because it's not, we don't have two bases here. When you have two bases that are the same, then you'd add their powers if they multiplied by each other. Then this becomes a to the power of 8. Okay, so similarly, this is going to become 2 to the 4 stays like that for now. This is going to become 3 to the 2 times 4. A power to a power, you use multiplication. So 2 to the 4 times 3 to the 8 as well. So when we simplify this, we have 2 to the 4 times 3 to the 2 times 4, because we multiply it when it's a power to a power. 2 to the 2 times 3 to the 10. Okay, then I'm going to simplify like terms. Okay, before we do that, let's just simplify even further. This is going to become 3 to the 8 divided by 2 to the 2 times 3 to the 10. Now, how do we simplify when we have multiple different terms and variables and numbers in division or multiplication? We sort of work with each like the like terms. So we're going to work with 2 as the base, and then we're going to work with 3. So now what rule are we following? Okay, remember we have the same base. We have the same base with different exponents. Okay, let's just maybe use numbers. A to the power of 4 over a to the power of 5. We have the same base, just with different exponents. So what do we do in this case? We say top minus bottom, 4 minus 5, which is actually equal to a to the negative 1. Okay, remember, okay, a to the negative 1, you could take it to the denominator to simplify it. It becomes 1 over a to the 1. Okay, we'll do this example here. So 2 to the 4, it's going to become 2 to the 4 minus 2 for the base of 2. For the base of 3, it's going to become 8 minus 10. Okay, so when we simplify this, it becomes 2 to the 2 times 3 to the negative 2. Okay, so how we can simplify this further if the question wants us, or we should generally we should try and leave our answer in positive exponents, or sometimes the question might specify, and then obviously in that case you'd leave it in positive exponent form, right? So this I could simplify as 2 to the 2 over 3 to the positive 2. So I'm taking this to the denominator, and that's what's making it positive. Okay, remember we discussed with this one. When you have a negative exponent, you can take it to the denominator or the numerator to make it positive. Okay, so we have 2 to the 3, 2 to the 2 over 3 to the 2. So this becomes 4 over 9. Simplified. Okay, so I don't know, what would you guys prefer? Completing these examples or at least starting number patterns? Okay, most people say we should start number patterns. Okay, so what I'm going to do is I'm just going to finish up. Someone wants me to just go through the last part one more time. So we'll do that, and I want to do at least 1/3 example. And then, yeah, we'll take it from there. Okay, so in this case, again, once we reach the stage, we're going to be following the rule of same basis. We'll just say 5, 2. Same basis, different exponent in division. So this, we keep the base the same and we subtract the exponents. Okay, and this simplifies in this case to 8 to the 3. So here, similarly, I'm going to be 2 to the 4 minus 2 and 3 to the 8 minus 10. So yeah, I get 2 to the positive 2, but yeah, I get 3 to the negative 2. So whenever I have a negative exponent, currently it's in the numerator because there's no fraction here, but any number can be a fraction if you just put it over 1 because it doesn't change the value. So I can take this to the denominator, it becomes positive 3 to the 2. Okay, let's do 1/3 example quickly. Let's do this example. So how do we simplify this example? Okay, it's quite simple, right? Remember, with thirds, right, when we have multiplication of thirds, we can work backwards and put each one under that third. So for example, this is 27 times x to the 9 times y to the 12. So this would become the cube root of 27 times the cube root of x to the 9 times the cube root of y squared. Oh, sorry, y to the 12. Okay, thereafter I can simplify. So this 27 cubed, sorry, the cube root of 27 becomes 3. The cube root of x to the 9, right? Remember, this is fractional exponent. So you can write it outside of the third, outside of this root. This is the third, the root symbol. Okay, so when we refer to third or root, we're just referring to that symbol. So when you're writing it outside of the third, you want to get rid of the third, you can write it as a fractional exponent, meaning your exponent needs to have a fraction, and its numerator is going to be the number inside, the exponent inside, and its denominator is going to be the exponent outside. So it becomes x to the 9 over 3, 9 over 3. And this one becomes y to the 12 over 3. Then when you simplify them, this becomes 3 to the x, 9 divided by 3 is 3, times y to the 4. We'll continue adding different bases, okay? With different exponents. Nothing. There's no rules to simplify these, especially the first one. This is completely unsimplifiable. You won't be required to simplify like this because, like I said, it's not simplifiable. This here, also unsimplifiable. So don't worry about those. Like if you're asking when you're adding exponents, different exponents, same exponents, because the shortcuts and the simplifications don't work when you add, because adding and subtracting is a bit more complicated. That's why we deal with multiplication and division. Okay, I just want to quickly do this one as well. So here I can separate it. It's 8 to the 15 times y to the 20. This can become the 5th root of x 15 times the 5th root of y 20. Then I can simplify it by changing it to an exponent, getting rid of the third and creating the fraction, 15/5 times y to the 20/5. Please remember, number inside becomes numerator, number outside becomes denominator. This is x cubed times x to the 4. No, y to the 4. Okay, so yeah, please complete the rest of the examples. Let me know how it goes. Let me know if you need help. Let's move on to doing some number patterns. Okay, let's talk about patterns with a constant difference. Okay, so what is a constant difference? If we try and identify the difference, so the difference here is always going to be, you're going to take your second term minus your first term. Alternatively, you could take any two consecutive terms, any two terms that are one after the other. Okay, and you say the bigger one minus the smaller one. So for example, I could say T3 minus T2, or T2 minus T1, or T50 minus T49. Okay, when I say T50, T1, T2, I'm talking about the term number. Now, this is T1, term 1, this is T2, this is T3, this is T4, this is T5. Okay, this is the fifth term. We refer to it as T5. Okay, the actual values of the term, like T1 is 2, T2 is 5, T3 is that, whatever, right? So now if we try and find the difference between them, we can do this. So T2 minus T1 is going to give me the difference. It's positive 3. T3 minus T2 is going to give me their difference, and it's also positive 3, and positive 3, and positive 3. Right, positive 3 because we're adding 3 each time. If you have different bases, you do times when working with multiplication. Different exponents or same exponents? If you have different exponents, you could simplify it. Sorry, if you have same exponents, you could simplify it to that. Right, this is rule number 6 or 5, I think 6. If you have different exponents, it's not simplifiable. You'd have to do this calculation individually. There'd be other ways to simplify, like other ways to simplify the question. Okay, so yes, constant difference means there's a constant difference between of 3, positive 3 between each term, right? So yes, now they want us to firstly state the next 3 terms. Okay, so we know that we have to add 3 each time. So we're going to add 3, we get 17. We're going to add 3 again, we're going to add 3 again. When we add 3 here, we get 20 and 23. So the next 3 terms, 17, 20, and 23. How did I get that? By simply adding 3 each time, because I noticed that's what the pattern was. Describe the pattern in words. Okay, someone describe to me this pattern in words, please. Okay, correct, but you need to add, you always say what you start. You always say what you start with, okay? So you say the pattern starts at 2 and then adds 3 each time to get to the next term. So it starts at 2 and you add 3 each time. Okay, write the general term for this pattern. How could we do this? Any idea? Does anyone have any ideas how to do this? How to find the general term, Tn, for this pattern? So when you talk about the general term Tn, you're trying to relate these numbers to the pattern. Okay. So you're trying to say that for any number, if you substitute into your general equation, you'll get the term. So this is number 1, 2, 3, 4, 5. So if you have, hey, have you guys learned the formula? Because I know that some teachers don't teach the formula. And then they expect you to. Okay, so that person that didn't learn the formula, I feel bad because these are very weird and annoying. Like, how are you supposed to know what does? Okay, so basically, like, for those of you who do have the formula, the people that are not allowed, the people that weren't taught the formula have to just figure out what changes made to 1 to get to 2, what changes made to 2 to get to 5, what changes made to 3 to get to 8, 4 to 11, 5 to 14, and it's the same change that was made to all of them. Okay, so I'm going to teach everyone the formula. Okay, if your teacher says you can't use the formula, you have a scrap piece of paper where you do your working out. I'm not telling you to cheat, I'm just telling you to use the formula. You do your formula and you get the equation and you write it down and you throw your piece of paper away and you tell them you used your head. But in the meantime, you use the formula because it's really silly that they don't allow you to use the formula. But the formula is really simple, okay? So whenever we have constant difference, right? We call this a linear pattern, okay, or an arithmetic pattern. But don't worry too much about the terminology; it doesn't matter. But it's when you have a constant difference mainly. Okay, when you have a constant difference, you can use the general formula Tn is equal to A plus D into n minus 1. Okay, so what exactly does this mean? Okay, A is our first term. So whatever your first term is, you're going to substitute it there. Okay. D is what we call the constant difference. Okay. N is the term number. Basically. Okay, so when we say the term numbers, notice there's two numbers here: 1 and 2, 2 and 5, 3 and 8, 4 and 11, 5 and 14. Now the term number is the red ones on top, right? Because that's telling me, okay, that's the term number that it is, meaning like that's first term, second term, third term, fourth term, and fifth term. Okay, so when we talk about n, right, that's what we're talking about. We're talking about that term number specifically. Okay, and then yes, the value of the term is this. The value of the first term is 2. Someone tell me what's the value of the fourth term? What's the value of the fourth term? Very good, right? And which term has a value of 20? Which term has a value of 20? Okay, correct. The seventh term. Okay, that's what we call it, the seventh term. So in that case, right, for 20, your n is equal to 7. Okay, for 20. However, actually, Tn is equal to 20. We'll discuss this because Tn, remember, n is the term number. So I actually should say T7 is equal to 20. Okay, where you can see I'm encompassing the fact that n is 7 here, but I know that I'm saying this is telling me that the value of the seventh term is 20. Okay, so for those of you who didn't learn it and you're not going to be given this formula, I would suggest memorizing this formula. It's not that difficult. You just repeat in your head like 50 times, you should know it. And then, yeah, this is what each of them mean. Okay, so let's do it in this example. I know time is up. We'll just continue a little bit extra and we'll end. Right? So write the general term Tn for this pattern. Okay, so firstly, my normal general formula is Tn is equal to A plus D n minus 1. Now, they want me to just have a formula for t, okay? And please note that when they want the general term, it needs to be in terms of n, meaning you need to have n as an unknown in terms of n. Okay. Yes, 3n minus 1 is the rule. Correct. You guys are correct. For all of you who said 3n minus 1, you guys are correct. Okay, they want it in terms of n. So in the general term, when solving for the general term, you'll always leave n as n. So I'm going to have tn. My first term, what's my first term in this pattern? My first term is 2, so I put 2 plus, what is my constant difference? Because that's what's next, d. My constant difference is positive 3. Please, the sign is very important. If it's negative, you put negative. So it's positive 3 times, and then I'll put n minus 1. Always leave n as n. Okay, so then this becomes tn is equal to 2. Now I distribute the 3 into the brackets. So I get plus 3n minus 3. Then this simplifies to tn. 3n I leave as 3n. It doesn't have any like terms. 2 minus 3. 2 minus 3 is minus 1. And I've solved for my equation. Okay, so you're following this formula. Now they say find the 20th term. Okay, so I'm asking you guys a question. Is this n 20, this number 20? Is it n or is it tn that they've given us? I don't know if this is a monkey see, monkey do situation, but it is not tn. Remember, guys, what is n? N is the term number. So aren't they talking about the term number here? The 20th term. They're not telling us that the value, or they're not telling us that, yeah, you see, here's the value of 140. Or even if they're not telling us that, well done. Okay. They're not telling us that, like, if I say they're not telling us that one more time, they're not telling us that, like, how do I describe this? They're not saying this term is 50 or it has a value of 50, because they don't have to say has a value of. They will, if they do, it's nice that they specify that. But like, they're not saying that this term is 50. Okay, when they say that, that's when they're giving you tn. That's when they're giving you the value of the term. Here they're giving you n. Okay, and n is the term number. And how do you know it's a term number? Anything that has these, I forget what you call these subscript things, 20th, 5th, 3rd, that's when you know they're giving you n. So n is given. So if they say find the 20th term in this pattern, and n is basically equal to 20, once I have the general formula, I can utilize it. Tn is equal to 3n minus 1. Okay, how do I utilize it? Isn't I want to get t20. So whatever term I want, I just substitute n as that number. So t20 is going to be 3 open brackets 20 minus 1, which gives me 59. Hope that makes sense. Let's look at number 5. Which term has a value of 140? So now tell me, have they given me n or have they given me tn? Remember, n is the term number, tn is the value of the term. Do I have n or do I have tn? Yep, that's exactly what you do it like for the person that asked. Correct, right? I'm glad we're all on the same page. Okay, so now we are given tn. Okay, because they're not telling us which they actually asking which term. Which term? They're asking what is n, basically. That's what they're asking. Okay, they're asking which term, and then you can answer it in English. Is it the 50th term? Oh, is it the 60th term? Is it the first term? Oh, they're asking for n. So you'd utilize your formula as well. Tn is equal to 3n minus 1. But this time you have the value of tn. You have the value of the term. Tn is the term, like the value of the term. So you substitute it there as 140. And this time you're solving for n. So you take n, you take 1 over, it becomes plus 1. So it becomes 141 is equal to 3n. And then n is equal to 141 divided by 3. 47. So it's like you divide both sides for 3, for those of you who prefer that. And then 47 is equal to n. So I'm just going to swap it around so it's nice. N is equal to 47. So which term has a value of 140? The 47th term. That's how our answer would be. So that's how we know we've answered for n. Okay, so unfortunately we have to end there. We couldn't get through to decreasing pattern as well as constant ratio. Okay, but what I'll do is I'll write out the formulas for constant ratio and you can follow the same logic. Okay, you can try to follow the same logic and you should be okay. If you guys have any issues before your exams, just message me. I will try my best to get your messages. I know I have a few messages that I haven't responded to, but yeah. Okay, so let's end it there, guys. Our time is up. I will see you guys next week, where I would like to finish up number patterns and I'd like to continue to do some more exponent examples. Okay, so yeah. Thank you guys so much for joining. Good luck. For those of you who are writing this week, all the best. Good luck. And I will see you guys next week. Same time, same place. Jazakallah khair. Thank you. Assalamu alaikum and goodbye.